The topic for today is Boltzmann statistics. This is classical statistical mechanics before we get into the quantum statistical mechanics. We'll be using the canonical ensemble, which we've mentioned before. This is a way that will enable us to take the microscopic predictions and be able to calculate macroscopic quantities from them. It's very, very powerful. It's also easier than the microcanonical ensemble that we have used up to now. In the microcanonical ensemble, remember, the system had to have an energy that was well known to within a very small range, and we were able to calculate all kinds of statistical quantities, thermodynamic quantities. But what we'd like to do today is use a different approach, and that is Boltzmann statistics. We are still very much using the fundamental statistical postulate, or the postulate of equal a priori probabilities, which just says that a system in equilibrium is equally likely to be in any one of its accessible states. That will continue to be true. In the case of the canonical ensemble or Boltzmann statistics, though, we often talk about a system in contact with a heat reservoir. And you might remember, we talked about heat reservoirs before. The heat reservoir is a system that has many, many, many more degrees of freedom than the system of interest. Oftentimes we use the reservoir to keep the system of interest at a constant temperature. So what we might ask ourselves is, under equilibrium conditions, what's the probability, we'll call it P sub r, of finding a system let's say, call it A, in state R, or microstate R, with energy E sub r. Okay, so that's what we're going to do. So here's system A, and what we're going to do is we're going to talk about an interaction with another system A prime. As I say, oftentimes we're going to use A prime as a heat reservoir, a much larger system. And in fact, let's do that. We'll call this a heat reservoir. It's got many, many more degrees of freedom than our system of interest. Let's look at some of the properties. So first of all, let's assume a weak interaction between A prime and A, such that we have a total energy, we'll call that E naught, which is just equal to the sum of the two energies. Let's call E prime for the energy of the reservoir, and we'll call it E sub r for the energy of our system. Okay, and so we're going to talk about the fact that the energy of the combined system will range somewhere between E naught and E naught plus dV. Now, let's say that A is in a definite state, say we know it is definitely in state R with energy E sub r, what that tells us is, in terms of the total number of accessible states of the combined system, that total number of accessible states, omega naught, would be equal to the number of combined states of the reservoir times 1, right? Because the state that system A is known. It's in only one state, and so my total number of accessible states is just equal to the total number of accessible states of the reservoir. That should be pretty obvious. Now, according to the postulate of equal a priori probabilities, the probability of occurrence in an ensemble where A is in a definite state R is just going to be proportional to the number of accessible states of this combined system. So that's to say that the probability that system A is in state R would just be equal to some constant times the number of accessible states of energy E sub r, or E naught minus E prime. I'm sorry, E naught minus E sub r. And we can determine the constant C prime by the normalization factor. That is to say that the sum of the probabilities, of course, of this distribution must equal 1. Let's specify the conditions a little bit further. System A is much smaller than system A prime. Therefore, we expect that E sub r is much, much less than the total energy of the combined system. In that case, what we can do is expand. Let's expand omega prime of E prime about energy E prime equal to E naught. So the way I can do that, I can write log of omega prime of E naught minus E sub r is equal to the log of omega prime of E naught minus, my Taylor expansion, d log omega prime dE prime times E sub r, plus higher order terms, which we can neglect because system A prime is so much larger than system A. Of course, you'll remember that this quantity here is what we have previously called beta, which is evaluated some fixed energy E prime equal to E naught. And it's independent of energy E sub r. Now, beta is related to the absolute temperature. Remember, we said that beta is equal to 1 over kT. So it's related to the temperature that characterized the heat reservoir. And also remember that the temperature of the heat reservoir is unaffected by its interaction with A because A is such a much smaller system. So I can write, as we have the, I can write that log of omega prime of E naught minus E sub r is equal to the log of omega prime of E naught minus beta E sub r. Or if I like omega prime of E naught minus E sub r, anti-logging, is equal to omega prime of E naught times E to the minus beta E sub r. But since omega prime of E naught is independent of r, I can write that the probability is going to be equal to some constant times E to the minus beta E sub r. If I normalize this to find the constant C, notice what I'll find. C to the minus 1 would be equal to the sum of E to the minus beta E sub r, sum over r, which tells me that the probability is going to be equal to E to the minus beta E sub r divided by that sum over r, E to the minus beta E sub r. So that is the probability of finding my system in state R and having energy E sub r. So what this is saying is if A is known to be in a specific state, the reservoir can be in any one of the large number of states accessible to it. Also, since omega prime of E prime is a very rapidly increasing function of E, we know this. What that says is, suppose A is in a state R such that, suppose, this is very unlikely, but suppose E sub r is greater than the energy of the reservoir. This means the energy of the reservoir is lower. The number of states accessible to the system is going to be markedly reduced by this factor. So the probability of encountering a situation like that, of course, is very much less. The factor, the quantity E to the minus beta E sub r is what we call the Boltzmann factor. And it's extremely important in the work that we're going to do. we call the expression P sub r equal to C times the Boltzmann factor. This is what we call the canonical distribution. And if I take an ensemble of systems, all of which are in contact with a heat reservoir of known temperature, we call this the canonical ensemble. And that's the arena in which we're going to make our calculations. Let's add some points to that as well. We can say the following. Suppose A is itself a large system, but much smaller than A prime. Omega of E is a very rapidly increasing function of energy. So omega of E is a rapidly increasing function of energy, but e to the minus beta E then is a rapidly decreasing function of energy, so that when we combine the two, notice what happens. We get a very, very sharp probability peak, a very sharp maximum in probability in equilibrium. The larger A becomes, the more pronounced the peak will be. Now, once you're able to determine what the probability is, we can do things the way we were doing them before. So for example, suppose I want to find the mean. Suppose I have some quantity y that I want to find the mean of. I can write that mean as sum over r e to the minus beta e sub r times y divided by sum over r e to the minus beta e sub r. Generally speaking, the denominator will be equal to 1 because it's normalized. So this is going to allow us to look at a whole bunch of interesting problems that we can solve using these techniques. The first one I want to do is one that we did in the last lecture, or a couple of lectures ago. In the microcanonical ensemble, I want to solve it again, but I want to use the simpler method of the canonical ensemble, and that is the example of paramagnetism. So you might remember we'll do the two-state paramagnet again, where we have we have a magnetic field, and we have a system where the spins either align parallel to the field or they align anti-parallel to the field. Those are the two possibilities. In this case, speaking quantum mechanics, so the magnetic moment vector is either parallel to B or anti-parallel to B. We call this case spin up, remember, and this is spin down when it's anti-parallel. We say that it has a negative spin when it's spin down, a positive spin when it is spin up. We've also talked about the magnetic energy associated with this. For a positive spin, it's equal to minus mu times B, remember, because it would actually be mu dot B, but they're aligned. For a negative spin, it would be a positive mu times B. So we might say then, using the canonical argument, the probability of the system having a spin up would be equal to C times e to the beta times the energy, which is mu B. I should say the negative energy, which is mu B. The probability of it having spin down would be some constant times e to the minus beta times mu times B. So notice, if mu is positive, the spin up state is the state with the lower energy. The spin down state is the spin with the higher energy. So we would expect that the lower energy state would be the one that's most likely to be found. If you have a whole bunch of spins, we might say that since the spin up state is more probable than the spin down state, maybe the mean magnetic moment for a bunch of spins would probably more likely point in the direction of the magnetic field than otherwise. Let's look at this a little bit more closely. Our significant parameter in this case is going to be beta times mu times b, or if you like, mu times b divided by kT. It's kind of a ratio of magnetic energy to thermal energy, if you will. Let's look at a couple of cases. Suppose we're at high temperature, so T is very large. If that's the case, y is going to be much, much less than 1. The probability that mu is parallel to b is almost the same as the probability of it being anti-parallel to b. So if that's the case, mu is considered practically randomly oriented, so that mu sub b would be equal to 0. Again, the upspins are as likely as the downspins. That means that that's almost like a random orientation of spins, which means that the net magnetic moment, or the mean magnetic moment, would be 0. On the other hand, suppose we're at low temperatures. Suppose T is small, which means that y is much, much greater than 1. Now it's a different story. Now I can look at the case that it's more probable that mu is going to be parallel to b than anti-parallel. Let's calculate what the mean would be in that case. This should be a familiar answer. My mean magnetic moment then would be equal to the probability of being spin up times the positive mu plus the probability of being spin down times the negative mu divided by, of course, the sum of the probabilities. I can write this as e to e beta mu b minus e to the minus beta mu b divided by e to the beta mu b plus e to the minus beta mu b, which you can recognize immediately is a hyperbolic tangent. So mu b is equal to mu times the hyperbolic tangent of mu b over kT. This is what we found before using the microcanonical ensemble, so it's not anything really new. The total magnetization then I could write as capital M, which is the total number, the total mean magnetic moment per unit volume. It should be in the direction of the magnetic field and should be equal to the number of spins I have, n naught times the mean magnetic moment. That's what I would expect to happen. And of course, that's what will happen. Let's see if we can bear this out. So let's go back to the case. We'll look at the high temperature case first. In this case, at high temperatures, y is much, much less than 1. E to the y then becomes equal to 1 plus y plus higher order terms. E to the minus y becomes approximately 1 minus y plus higher order terms. So for y much, much less than 1, we expect that the hyperbolic tangent of y would be equal to 1 plus y plus higher order terms minus 1 minus y plus higher order terms divided by 2, which everything else cancels except I've got 1 minus 1, I've got plus y and a minus y, which just gives me y. So that's what I would expect for very high temperatures. For low temperatures, e to the y is much, much greater. So for low temperatures, y is much, much greater than 1. E to the y is much, much greater than e to the minus y. which tells me that tanh of y is going to be equal to 1. So our qualitative predictions will actually check out. So when mu b over kt is much, much greater than 1, we have the case that mu b, the mean magnetic moment is mu, so they're all going to be pointing upwards, or more likely to be pointing upwards. When mu b over kt is much, much less than 1, mu b then, mu sub b mean will be equal to mu squared times b over kt. My mean magnetization will be equal to some concept we'll call chi times b, where chi is the magnetic susceptibility. In this case, chi is equal to n naught mu squared over kt. And we notice that chi is proportional to 1 over t, which is what we talked about earlier. It's called Curie's law. This inverse proportionality to the temperature and the magnetic susceptibility. On the other hand, if mu b over kt is much, much greater than 1, then the total magnetic magnetic moment would be n naught times mu, because the expectation would be that more of the spins would be pointing upwards. Look at a graph of this as well. So suppose we were to plot, on the x-axis we have mu b over kt, so the magnetic energy versus the thermal energy. And here we'll plot the mean magnetization divided by n naught over mu. And that's 0.5, and that's 1. So we have at the start, this is linear, and it's proportional to the magnetic field. And then it will curve on over and asymptotically approach 1 as we go to higher and higher temperatures. So that's a nice example of how we can use the canonical ensemble to calculate a mean magnetic moment or magnetization. As it turns out, you might remember, it's easier to do this than to count states the way we did in the microcanonical case. Let's do one more example in the time we have left. Let's talk about a molecule in an ideal gas. So we'll start with just one molecule. It's actually complicated enough. Suppose I have a monatomic gas. It's at temperature T. It's in a container of volume V. And let's assume that the interaction between all the other molecules is very weak. I can say that the total energy of that system is just going to be equal to the sum of the energy of each of the individual molecules, which should all be kinetic, right? There's no potential energy in this case. So the way we look at this system is one of the gas molecules will be the system, and the rest of the gas molecules will be the reservoir. The energy of that molecule, of course, is purely kinetic. I can write that as p squared over 2m. And the position of the molecule will range from x to x plus dx, y to y plus dy, z to z plus dz. Momentum, as well, ranges from px, py, pz goes from px to px plus dpx, and etc. for y and for z. So if I were to look at the volume of phase space that's occupied by this one particle, I might write that as d3r for the position, d3p for the momentum, and I could write that as dx, dy, dz, dpx, dpy, dpz. And we might ask ourselves, what is the probability that the molecule will lie between R and R plus dr, and have momentum between P and P plus dP? Well, what we would do is multiply the probability that the molecule is found in a particular cell by d3R, d3P, divided by H naught cubed. And so the probability then of it being found with those coordinates and momenta would just be d3R, d3P times, so it's d3R, d3P over H naught cubed times e to the minus beta p squared over 2m, where p squared over 2m is the energy. Notice that the probability doesn't depend on R. If I have no external forces, I don't have to worry about the position. So the only thing that I'm going to have to worry about then is the momentum. So if I want to find the probability that the particle's momentum lies between P and P plus dP, I can write that as probability of that times d3P. It's just going to be equal to, or just be proportional to, e to the minus beta p squared over 2m d3P. We can equally express this in terms of the particle's velocity.
We have 20 seconds, Dr. Blows.
Which I can write as c e to the minus beta mv squared over 2, doing it in terms of velocity, d3v. C is a constant of proportionality.